Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Hello, I'm Dave Whitehead, CEO at Schweitzer Engineering Laboratories, here with Dr. Ed Schweitzer, President, Chief Technology Officer, Chairman of the Board, and founder of SEL. Ed holds the grade of Fellow in the IEEE, a title bestowed on less than 1% of IEEE members. In 2002, he was elected as a member of the National Academy of Engineering. In 2012, he was awarded the Medal in Power Engineering, the highest award given by IEEE, for his leadership in revolutionizing the performance of electric power systems with computer-based protection and control equipment. In 2019, Dr. Schweitzer was inducted into the National Inventors Hall of Fame for his invention of the first digital protective relay. Ed is truly a recognized pioneer in digital protection. SEL has a 35-year history of inventing new ways to make electric power safer, more reliable, and more economical. The company has grown from Ed being the only employee working in his basement to a company of over 5,200 employees around the world developing products and providing services used in the monitoring, protection, and control of electric power. While many of us have seen Ed speak at conferences on any number of technical subjects, I thought it would be fun to sit down with Ed and get his thoughts on a range of topics, including innovation, simplicity, how SEL came about, entrepreneurship, cybersecurity, and economics, to name just a few. Today, Ed and I will be discussing innovation, creativity, and simplicity. Welcome, Ed.
Thank you, Dave. It's a pleasure to be here.
All right, let's get started with innovation and creativity. I bet everyone who's met you has wanted to ask, but maybe was a little bit too shy, what was the spark, the creativity and innovation for the first product SEL created?
You know, sometimes it's hard to find out exactly a spark, but there's, a little trail, and the beginning of that trail was coming to Washington State University to study a PhD in electrical engineering. And when I registered for my classes, they said, be sure to take protective relay. So I said, okay. So I thought of relays as these little attracted armature things. That's not going to be very interesting. I signed up, this is what my advisor told me to do, and went to the bookstore, bought the book, started reading it, and could not put it down. So I became so intrigued about these special purpose signal processors. And wow, all these fabulous characteristics that the designers of these protective relays had formed using electromechanical and some solid state ideas that are really nothing. I guess I realize that they're special purpose signal processors. Special purpose signal processors that look at the voltages and the currents of the power system, and they make a decision in as little time as practical, just whatever time it needs to make sure it's right, in order to trip a breaker or not. And to do this continuously around the clock, and when something bad happens on a power system, to be able to trip the breaker in milliseconds. And I thought, wow, is that fascinating? And then what built on that was one of the foundations for that was in work I had done in a previous employment that I had learned a lot about digital signal processing, which is pretty new at the time. And on top of that, the microprocessors were just they were emerging, changing from the little 4-bit things to 8-bit things and small memory spaces and emergence of better and better analog to digital converters. And I started thinking, wow, why couldn't we make digital protective relays using pulling these things together? The need for electric power system protection is presently, in those days, embodied in the electromechanical and solid state designs, and seeing if we couldn't make it better and do new things using digital signal processing and the microprocessors. That's more of a, I don't know, a slow burn than a spark, Dave. But, hope I'm answering your question.
You're doing a great job. I want to follow on that thread just a little bit. So you were coming up with the microprocessor-based relay. There was certainly the traditional electromechanical relays. You pointed out microprocessors were just emerging at the time. There was certainly an opportunity to merge these various technologies all into one. And so the question really is, you've got over 200 patents, which is truly amazing. And following along, seeing these opportunities, how do you come up with the idea to merge the electromechanical technologies with the microprocessors? Is there a process to how you go about with this invention or creativity, or does it just happen? It just something goes off in your head, or is it if you exercise it, like if you exercise enough, do you get stronger, and that's the way you go about invention, or is it something of both?
Well, I think that inside everybody there's creativity. A lot of that is sort of designed out by our needs to be socialized. I like to say, look how creative a 2-year-old is, and somebody asked what my first creative act was, and I thought for a second, I remember answering that it was probably whatever I did right before my parents told me no for the very first time. So this kind of creativity is in all of us, and then through school and parenting and so forth, we have to learn to channel it, and maybe sometimes in the process we suppress it a little bit. And I think there's a human need to be creative, and either we're going to express that need and satisfy that need at work or at home through things that we're doing, or at work, or maybe hobbies or social activities in our the rest of our lives, and it'll find its way out. I saw my father be inventive, and that was a really, really good, positive, strong example. But to me, it's always intriguing. Like, well, how does something work? And can I find a better way? When's the last time somebody ever looked at this problem? If it was some of the things that are really ripe for invention, are areas of science and technology that haven't been touched for a long time. When I looked at the electromechanical protective relays and started to realize that, wow, a lot of those ideas went back to the 1920s, and of course things had moved on, but in technology and electromechanical relays and the solid state stuff in the 70s are sure a lot better than they were in the 20s, but it was still kind of based on the same measurement principles, and maybe there was a chance for something new. So looking for that. It's if you go to a restaurant, of course we'd all like to go to a restaurant, but if you go to do carry out from a restaurant, well, maybe you look over the menu and say, I'm going to pick something new, because we like that kind of variety.
Hey, we're recording this episode on April 22nd, just to put into context. A few weeks ago in the Wall Street Journal, there was an article describing how a lot of innovation was coming about to address the global pandemic. There's this old saying that necessity is the mother of invention. However, are we being more creative now because of a time of stress, necessity being the mother of invention, or do you think maybe it's in part because we're going to be a little bit more acceptable of failure? We're kind of in, I won't use the word dire straits, but something, there's a need and a rush to get stuff done. So maybe in traditional ways, we would put something off or not do something because we're afraid of failure or something like that. What are your thoughts on this renaissance, if you will, of innovation and creativity during the COVID-19 that we're all experiencing.
I'm glad you brought it up, David. It's just absolutely magnificent how companies like Ford and GM are making ventilators. How I think there's 20 different outfits working on treatments, and another 40 that are working on diagnostic tools, and a lot more laboratories that are involved in this. Here in our own community, the Washington State University Veterinary Medicine Department has a wonderful testing capability for viruses, and our community is pulling together to figure out how can we use that testing capability that we already have in our community to get a better understanding of the virus and its antibodies right here. So all of this creativity does come out more. Necessity is the mother of invention. And, there is a drift to sort of a contemplative, steady state, where people sometimes in more calm times, I suppose, are looking to government and policymakers and considering a whole bunch of outside factors. But when an emergency like this virus comes along, it's all hands on deck to fight the fire. And guess what? All kinds of creativity does come out. There's people who are looking at this coronavirus who, like me, who didn't have an idea what a coronavirus was at all. I'm not sure I have much of an idea, but all of our creativity is coming out. I mentioned Ford and GM making ventilators. Well, guess what? Ford was making airplanes and GM was making tanks, during World War II. And our country does have this way of coming together in probably a better way because of our free society than any other country on the face of the earth. It makes me real proud to be an American.
It's amazing. Certainly the COVID-19 is a terrible thing for our country, but on maybe the silver lining is that all the innovation that gets unleashed for everybody in all different types of sciences and around our communities coming together to solve this truly challenging problem. I'd like to move on now to simplicity, which I think is the cousin to invention and creativity. I've been in hundreds of meetings where we're kicking off a new project, and invariably you remind us to start with first principles and keep it simple. Have you always stressed simplicity?
Yeah, I think I have, Dave. It's almost a process of learning. That how do you really, when you start to learn about something new, that at first it's complicated, it's foreign, and sooner or later, just in the process of learning and understanding, you get down to what is, the first principles behind whatever it is. And I think that leads to simplicity. And Dave, how much we like to talk about Einstein, everything should be as simple as possible, but no simpler. And Da Vinci, who said simplicity is the ultimate sophistication. So these philosophical looks at it are important. But when we can boil something down to it's simpler or find a simpler way, we know it's a better way. And we know that is also something that being better will benefit more people. We can make it cheaper at a higher level of quality, make it more accessible to more people, and be of more service in our world than any other way. If something is complicated, it's vulnerable. Looking at the other side of the coin here, and say complexity is sort of the opposite of simplicity. And things complex are things that fail. That if I'm going to try to, you're going to try to explain to me how something complex works, I may lose my patience with the idea at some point through the description because I can't follow it. And on the other hand, if you make it simple, and if what you're presenting is simple, and then your solution is simple, I'm going to at first be very intrigued with it and say, Dave, it can't be that simple. And then you say, well, it is, Ed. Look, well, watch this thing work. And then I'll say, wow, that's impressive. It is that simple. So it's very, very intriguing, compelling, and valuable simplicity.
Have you ever tried to quantify simple? You know, it's kind of an abstract term, and maybe it's like art. It's in the eye of the beholder of what simple is. But I've always thought, how do you quantify or describe to somebody what is simple? And maybe you have some thoughts on that.
Well, the long pause I'm putting in here, Dave, says, no, I have no clue how to quantify simplicity.
And that's totally okay.
There is ways of quantifying complexity. You know, if the parts list gets too long and the schematic covers too many pages and there's too many screws holding the assembly all together to build it or service it, well, then it warrants or if there's too many PEM nuts pushed into the chassis. As you know, sometimes we've taken things apart and counted all the PEM nuts and said, why on earth do we have all those fasteners in there? Let's see if we can do it less. I was restoring an old radio that's as old as I am, and to take this thing apart, the thing was certainly not designed to be easily serviceable. You know, I had a big bowl of screws that I had taken out of all kinds of different sizes, shapes, and lengths in order to get inside this thing. And that's all I was thinking about. My goodness, didn't anybody stop to think about the person was going to have to go in there to change a capacitor or adjust a coil or something? Yeah. So just looking at it like that, we got to make it simple for our people in manufacturing, for our customers, for ourselves. If you put too many parts in it, you're going to have a supply chain problem. And then when it comes to software, the more complicated we make it, the more vulnerable it may become. And gosh, one of the famous companies that makes a lot of cellular telephones that's been held in very high regard for its cyber security. Well, there's a security vulnerability in the way that it manages email. And my goodness, who would know? The phone on the outside looks so simple, but on the inside, it's a huge software system. In fact, I've lost track of how many radios are in the thing, too. So this complexity, especially when it's hidden, it's sort of like an iceberg that it looks like a little tiny thing on top, but all this hidden stuff is just a disaster waiting to happen.
I think the term that we've used, and as I recall, you're not necessarily a fan of it, complexity, right? From the outside, perhaps it looks simple, but as you pointed out, you open up the hood, and oh my goodness, there's a lot of complexity behind some solutions. Yeah,
if you open up the hood and say you don't want to tell your mama what's inside that thing, you know you got a problem.
So that leads me to my next question then along those lines is, have you ever been working on a problem where at some point you've kept adding things, features perhaps, or another radio or something like that to overcome a deficiency or address a customer request or something like that, and then all of a sudden you'll look at what you've built or what you're working on, and the system or the product is no longer simple, and you spent a lot of your good time and put your heart and your soul in it. What do you do to address that kind of condition? Do you throw everything away? Do you start? I think we've all ran into those kind of problems before.
Well, You know what? We're going through one right now with the RPM. And it starts out as a simple idea, and then we all have ideas that to make it even better. And pretty soon it's becoming complicated, more expensive, maybe some testing problems, out of everybody's best intentions to put alarm contacts and LEDs and other features on the thing that should make it more attractive to a user, but may actually be taking away from the very value that the product would present to a customer. So what do you do? That's your question. What do you do when that happens? You got to step back. And I'll tell you what, I've worked with some of the most wonderful young engineers who are perfectly willing to do that. They say, yeah, let's do. And they're open to it and embracing it. And I haven't heard any of them say, oh, Ed, if we just keep going this way, we're going to get it done sooner. And they are fully embracing the challenges of making it as simple as possible, but as Einstein said, no simpler. It's an exciting pursuit, and we did need to take a few steps back. And I haven't heard anybody complain. Nobody's come in my office and called me a naughty name or anything.
I think that has a lot to do, though, with the culture you set up, though, too, Ed, from the folks doing the work to the folks directing the work, right? When it's allowing the freedom or the opportunity to step back and say, you know what, this is not working, instead of pushing forward to try to get something done, let's do it right. And
what's funny about it is some of that complexity that went in there, I caused it. It was my bad.
Well,
that in other parts of it, I went right along with it, but at least at some point we all had the ability to step back and say, this isn't quite going the way we thought it was. And I was so grateful that Krishna, the project manager, he understands all this. He understands the true essence of what we're trying to do, the new thing we're trying to do. And he isn't trying to say, come on, Ed, we've all agreed to this. Let's just get it done now. So we're all going back here and say, this thing is going to be beautiful when it's done.
That's
and
a lot.
We don't know exactly what it looks like. And I guess that's part of the challenge, the risk we take, and also the reason that there's a moral justification for making a profit at the end of the day, because we went through all that process.
That's a great answer. Here's a fun question, so think about this one. The T400L is based on traveling wave principles. While the principles are pretty straightforward, to implement the principles required a lot of hardware and software. The T400L has a lot more stuff under the hood than the SEL21 did. Is the T400L simpler, more complex, simplexer, I think I just created a new word, than the SEL21?
Well, first of all, uncreate that word simplexer, please, Dave.
All right, it's stricken from the SEL language.
That's right. And is it simpler? Well, the principles are, in general, simpler. The late Jules Estergalio, the engineer at Bonneville Power Administration, he liked to say he loved traveling waves because all he had to deal with was resistances and not complex impedances. And it's a very, very good point that he raises. So instead of phase shifts, we're more concerned about modal decomposition, and so the whole thing does get simpler, a lot simpler. On the other hand, there's aspects of it that do get more complicated. I mean, in order to pull off a traveling wave relay, you have to sample every microsecond. It's not good enough to sample every millisecond. So you have to sample, say, 1,000 times faster. Is that more complicated? Yes. Is it allowed by the technology of today? Yes. Is the relative complication in today similar to the level of complication 30 or 40 years ago when we started this stuff? Yeah, it certainly is. We have achieved the ability to rather simply sample at a megahertz today. We're sampling at a millisecond, or 1,000 times slower. 40 years ago is about as the best we could do practically. So, time does march on. We do need to take new looks at things. And in fact, as you know, Dave, that Tony and you and I actually, it was about 6 or 8 months ago, we said, wait a minute here, what could we do to make a protective relay that didn't use a computer in it? Now, Our company is based on sticking a computer in a box and turning it into a relay. But then we also know that because of the complexity, that sometimes it is simpler to do something in analog than to do it digitally. So why not look at that? Why not be curious about that? Because there's nothing carved, on the 11th through 15th commandments, for example, that says thou shalt only make digital relays digital from here on out. No such thing. There's no secret codicil in the forming documents of SEL that says we're only going to do it if it's digital. If you can make a better relay out of oatmeal, we got to use oatmeal.
And that's really one of the fun things about working here at SEL. We spent the last 5 or 6 years, developing and perfecting traveling wave technologies that we can now is being deployed around the world and really benefiting our customers that are putting the relays on their systems. But it's really interesting too to step back and say, hey, how else can we do it, right? And have that encouragement certainly from the chief technology officer. Great, we did that. How else might we go about protecting power systems? It makes working here certainly a lot of fun. Ed, thanks so much for spending a little time with us today talking about innovation, creativity, and simplicity. And I'm looking forward to talking to you again about other topics.
This is a lot of fun. Thanks, Dave.
Our pleasure. Talk to you later, Ed.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.